Students, today we will solve the exercise problem 1.1. Here we have to find out the HCF of these two numbers 135 and 225. And second question is 867 and 255. First one 135 and 225. Here by seeing these two numbers, we get to know 225 is greater than 135. We have to apply Euclid's division lemma. Apply Euclid's division lemma. I have already told that EDL is Euclid's division lemma for 135 and 225. Here, we will solve this by long division method first. 135 into 135. 5 minus 5 is 0. 12 minus 3 is 90. Here, 0. We didn't get R as 0. So, again we will apply Euclid's division lemma for 135 and 90. 90 into 1. 90, 5 minus 0, 5, here 4 we will get, and this is also is not 0, R is equal to 45 we got. Here again we should apply Euclid's division lemma for 45 and 90. 45 into 90, 0. Here R is equal to 0. We will stop the long division method. What we have done? Apply Euclid's division lemma for 135 and 225. Here A is 225 and B is 135. Here what your Euclid's division lemma says? A is equal to BQ plus R. A is 5 is equal to B is 135 into what we have done there? 135 into 1. How much will be the remainder? 90. 90 is the remainder. Here R is not equal to 0 because R is 90. Then again we have to apply Euclid's division lemma for 135, that is your B and this is your R, for B and R, 135 and 90. How much we get? 135 is equal to 90 into 1 plus 45. Again we have to apply Euclid's division lemma because R is not equal to 0. That is 90 equal to 45 into 2 plus 0. 45 to 2 plus 0. Here what we got? 45 is a therefore 25 and 135. First we have to do long division method up till we get R is equal to 0. Then we have to write it as Euclid's division algorithm by using Euclid's division lemma. Apply Euclid's division lemma for these two, where this is your A and this is your B. A is equal to BQ plus R is Euclid's division lemma. Then 225 is equal to 135 into 1 plus 90. Then again this here R is not equal to 0. R is not equal to 0. Then again we have to apply Euclid's division lemma for B and R, 135 and 90. Then again we will get R is not equal to 0, R is equal to 45. Then we apply Euclid's division lemma for 90 and 45. 90 is equal to 45 into 2 plus 0. 0 as remainder. Then we will stop applying Euclid's division lemma. Then 45 will be your HCF. Your first second question. Is 7 and 255. First we will write 867 is greater than 255. 867 is greater than 255. Here we have to apply Euclid's division lemma for 867 and 255. We have to apply Euclid's division lemma for 867 and 255. Here A is your 867 and B is equal to 255. First, 867 is equal to 5. 255, 3 5 15, 3 5 15, plus 160, 3 2 6, plus 7. 7 minus 5 is 2, 6 minus 6 is 0, and 8 minus 7 is 1. We got 1 or 2 as remainder. So that is not equal to 0. Then again we will apply Euclid's division lemma for 255 and 1 or 2. 1 or 2 into 2. How much you will get? 2 not 4. 255 minus 2 not 4. How much we will get? 1 and 51 we will get. This is also not equal to 3. This R is not equal to 0. What your Euclid's division lemma says? Until we get R is equal to 0, we have to apply Euclid's division lemma for the numbers. We will get step by step as B and R. Here B is your 1 or 2 and R is your 51. Then we have to apply lemma for 51 and 1 or 2. Here 51 into 2. That is 1 or 2. We will get 0 as remainder. And we will stop the division method. Here we have written A is equal to 867 and B is equal to 255. To simplify 867, what we have done, we will write that in Euclid's division lemma. That is A is equal to BQ plus R. First we will write what is Euclid's division lemma. That is A is equal to BQ plus R. Your A is 867 and B is 55. And what is quotient there? Quotient is B. Plus remainder is 1 or 2. Remainder is 1 or 2. Here, remainder is 1 or 2 means again we have to apply Euclid's division lemma for B and R. We have to apply for B and R. Here B is 255 and R is 1 or 2. That is 255 is equal to 1 or 2 into, what is the quotient here? 1 or 2 into 2 plus how much you got as a remainder? 51. Again, here it is not 0. Again we have to apply Euclid's division lemma. That is for 51 and 1 or 2. 51 and 1 or 2. 1 or 2 is equal to 51 into 2 plus 0. Here we got 0 as remainder. Then we will stop applying Euclid's division lemma. 1 or 2 is equal to 51 into 2 plus 0. Here, when What your Euclid's division algorithm says in last step? If we get R as 0, then B is your HCF. This is A, B, Q, R. Then B is your HCF. So then 51 is HCF of 87 and 255. 51 is HCF of 87 and 255. We have to solve much more problems on Euclid's division lemma and Euclid's division algorithm. Then only get a clear picture of both the algorithm and lemma to solve HCF of your numbers. Second question. Show that any positive odd integer is of the form 6q plus 1 and 6q plus 3 or 6q plus 5, where q is the integer. What they have asked? Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Here, they have given odd positive question number 3. Odd positive here 6q plus 1 or 6q plus 3 or 6q plus 5. We have to show that every odd positive integer will be in the form of 6q plus 1, 6q plus 3 and 6q plus 5. For solution, we have to write Euclid's division lemma as A is equal to Q plus R. Here B is your 6. B is equal to 6. R is varied because here R is 1, R is 3 and R is 5. R can be 0, R can be 1, R can be 2, R can be 3 and R can be 4, up to R can be 5. First, R is equal to 0. How will we write it in the form of Euclid's division lemma? If R is equal to 0, A is equal to B is 6. 6q, R is equal to 0. Then what we will get? 6q. If R is equal to 1, if R is equal to 1 means A is equal to 6q plus 1. Again, if R is equal to 2, how much you will get? A is equal to 6q in the R is equal to 2. R is equal to 3. Already you know. A is equal to 6q plus 3. If R is equal to 4, A is equal to 6q plus 4. Then if R is equal to 5, how will we write? A is equal to 6q plus 5. These are the integers, some integers. Here 6q, how do you write this? 2 into 3q. You can simplify 6q as 2 into 3q. Then if we multiply 2 with any number, we will get a even number. We will get even number. Here we added plus 1. So this will be odd positive integer. This will be your odd positive integer. Here 6q is, we already know this is even. Q is even and this q is also even. Then what we will get? Even positive integer. 6 cube plus 3. Here 6 cube is even and 3 is odd. Then we will get odd. Odd positive integer. Then here also 6 cube is even number. 4 is also even number. Then we will get even number. Here 6 cube is even. Then 5 is odd. What will we get? Finally, we will get odd positive. Here 6 cube plus 1 is also odd, and 6 cube plus 3 is also odd, and 6 cube plus 5 is also odd. What they have told you? We have to prove that. Show that 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5 are all positive integers. Now we will show 6 cube plus 1 and 6 cube plus 3 and 6 cube plus 5 as all positive integers. Second question in the exercise. Now we will solve third question. An army contingent of 660 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? They have given the total number of members and they have given the members in a column, and they have asked you to find out the number of columns that total number of members can march. And the 32 members. Total number of army members is 616, and the members in the army is parade is 32. The total number of army members equal to 660, and the number of members in parade on column 32. Divide 660 in a columns. How many columns we have to do with the 32 members they are asked? We have to find the HCF of 660 and 32 to find out the columns of the members. Here 616 is greater than 32. 616 is greater than 32. Then we have to apply long division. What is 32 into 1? It is a 24, 25, 9 is a 9 is a 8, 9 is a 27, 28. 288 will get. So 32 into 9, 9 is equal to 288 will get. 60 minus 8 is 8, 9 minus 9 0, 2 minus 2 0. Here we will apply for 8 and 32. If we apply the distribution lemma for 8 and 32, then 8 into 4, 32, we get 0. As a, then we will stop the long division method. Here Euclid's division lemma for 16 and 32. How much you will get? For 16, 32 into 19 plus remainder will be 8. Again we have to, remainder is not equal to 0. Then what we have to do? We have to apply Euclid's division lemma for B and R. Wherever I have written linear, that is Euclid's division lemma. Here to get 32, what we have done? 8 into 4 plus 0. Here we got 0 as a remainder and 8 is your x here. Then they will do 8 columns of 32 members to divide 616 members of the RB group. 8 columns for the number 8 columns. Divide 16 members in 8 columns. Every column will be having 32 members. Your third question. Now we will see fourth question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. We have to show that the square of the number is of the form 3m or 3m plus 1 or 3m and 3m plus 1 for some integer m. Directly we can't take 3m and 3m plus 1. We will take 3q. A is equal to 3q plus r as a some positive integer. Some positive integer. For this, we have r as 0 and r as 1. R is equal to 0. Then A is equal to 3q plus r, where r is equal to 0. 3q plus 0, you get 3q. What they have asked? They have asked us square of the number. Square of some integer will give you a 3m or 3m plus 1. We have to square on both sides. Squaring on both sides. Here we will get a square and 3q whole square. 3 3 is 9, 9q square. We have to write in the form of 3m. So, take 3 outside. We left out with 3q square. This 3q square, we write it as m. Then, this is equal to 3m. 3 into 3q square, we can write that as in the form of 3m. Then, if r is equal to 1. If r is equal to 1, A is equal to 3q plus r. Here r is 1. Then a is equal to 3q plus 1. If we square on both sides, squaring on both sides, what we will get? A square is equal to 3q plus 1 whole square. Here, apply a plus b whole square formula. You already know that a plus b whole square is equal to a square plus 2b. Here, a is your plus 2 into 3q into 1 plus 1 square. How much we will get? 3 into 3 9, 9q square plus 2 into 3 6, 6q plus 1. We will write this in the form of 3m plus 1. So, we have to take 3 outside and 3 to the 9, 9q square plus 3 into 2, 6, 2q, and we don't have any common factor from 1, right? This is 3m plus 1, where m is 3q square plus 2q. We wrote this sum integer in the form of square of the same integer in 3m form and 3m plus 1 form. What we have told? They have asked us to show that the square of any integer is in the form 3m or 3m plus 1 for some integer m. For some integer, here m is some integer, 3q square is some integer, 3q square is 2 is some integer. This is your fourth question. And you have similar question. Next question is similar to fourth question. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Here they have asked us to show that cube of, that is the square of, here cube of some integer 9m or 9m plus 1 or 9m plus 8. Here again, by applying Euclid's division lemma, take a is equal to 3q plus r. Here b is 3 and r can be 0, 1, 2. If you apply, if r is equal to 0, then a is equal to 3q plus 0. Then a is equal to 3q. We have to do cubing. Cubing on both sides. A cube is equal to 3q whole cube. How much you will get? 3 into 3 into 3, 27 cube. Get 27 cube. If r is equal to 1, then how will you write? A is equal to 3q plus 1. Again, we have to do cubing on both sides. A cube is equal to 3q plus 1 whole cube. We have to simplify this 3q plus 1 whole cube. 3q is equal to 3q plus 1 whole cube. We know that A plus B whole cube is equal to AQ plus 3AB into A plus B plus AQ. You know that A plus C whole cube is equal to AQ plus 3AB into A plus B plus BQ. Here we will simplify this 3Q plus 1 whole cube. A is Q, 3Q whole cube into 3Q into 1 into 3Q plus 1 plus PQ means P is your 1 is your P. Then 1 this 27Q cube plus 3 into 3 9 9Q into 3Q plus 1. We have to simplify this. We have to write simplified form at the end of the equation. 27Q cube 9Q into 3Q 27Q square plus 9Q into 1 9Q plus 1. Here we have to write this in the form of 9m plus 1. Then take 9 outside and write remaining the bracket. 9 into 3 3q plus 9 into 3 3q square plus 9 into 1 that is 1q. Here there is no common factor. Then I will write plus 1 as it is. We take this for in m plus 1 where m is equal to plus q square q. And again we are going to solve to get 9 plus 8. This is for 9 plus 1. Equal to 6. A is equal to, we can write in the form of Euclid's division lemma plus 2. We have to cube on both sides, cubing on both sides. We will get A cube is equal to 3 cube plus 2 whole cube. Then again we have to apply A plus B whole cube is equal to 3A cube plus 3AB A plus C plus B cube. Here B cube whole cube 3 into 3 cube into 2 into 3 cube plus 2 plus 2 cube. We write this 27 q cube plus 3 into 3 9 9 into 2 80 cube plus 2 plus cube. Here 27 q cube plus 18 into 3 54 54 q square 18 into 2 36 cube plus 2 cube. 2 cube is 8. 2 into 2 into 2 we will get 8. This will take 9 as common factor. 9 is 27. Then we left off with 3 cube cube plus 9 into 6 q square 9 into 4 4 cube plus 8. Here we will get 9 m plus 8. M is equal to 3 cube plus 6 cube square plus 4 cube. Here, yeah. Here